All right, in this set of notes, I'm going to be talking about three topics: sampling methods. This is a topic we touched on very early in the course, and the distribution of sample statistics, and finally the central limit theorem. So keep in mind, one of the main uses of statistics, or in particular inferential statistics, is to estimate the value of something that we can't necessarily calculate. So the way we apply statistics is we choose a population that we want to analyze. We select a sample from that population. We collect data from that sample. We calculate our sample statistics, and then we use them. We use these guys to estimate the value of a parameter. So if you think about what is statistics, well, statistics is the collection, organization, analysis, interpretation, and presentation of data. That first step, the collection, if data is not collected in the right way, no amount of statistical analyses is going to draw any meaningful conclusions because the original data is tainted. So I want to talk specifically about what it means for a sample to be random or a simple random sample. This is our goal. So the first step of applying statistical analyses is to collect data. When you're collecting data, it has to be done in a random way. Randomness is the most important aspect of the statistical analyses. If the data is not collected in the right way, the whole analysis is potentially will potentially yield flawed results. Okay, so different textbooks define this idea of a simple random sample slightly differently. Both of these definitions are basically the same. So these are the two most common definitions of a simple random sample. We say a sample is considered to be simple and random if every member of the population has an equal probability of being selected as part of the sample. Or each sample of size n has an equal chance of being chosen. So if you think about this first definition, when would every member of the population not have an equal chance of being selected? Well, if you were to survey adults living in Boston and ask the question, how many parking tickets do you have on average per year? If you were to take the T, get off, let's say, in Copley Square, and just stand outside the T stop, if you were to ask, people passing you by, if you were to ask just one question, how many parking tickets have you gotten this year? Well, everyone in the population does not have an equal chance of being selected there. So if you're right outside a T stop, then you're more likely to be asking people who don't have a car because they're taking public transportation. If you were to drive out to, I don't know, somewhere a little bit outside of the city, very far from a train station or a bus stop, and you were to ask people how many parking tickets have you had this year, you will get completely different results, because in the first case, you're likely going to have less people that drive than in the second case. Anyway, the point is, when we sample from a population, we want to make sure it's done in a simple and random way. So we've talked about this before. Just the way you phrase the question could affect the responses you get. Whether or not the responses are anonymous, that's a very influential factor. People tend to be more honest in an anonymous survey than if the person asking the questions knows which person gave what responses. So if a sampling method is not done in a simple random fashion, we say it's biased. In some way, the way you phrase the question or the people you chose to ask affects the sample statistics that you obtain. We want the sample to be representative of the population. This is the key. Like for the whole statistical analyses that comes after the sampling, for any of that to have any meaningful results, the sample needs to represent the population. So excuse me. The following are a few methods for obtaining a sample that is close to or is simple random. So one method is systematic sampling. You could take in this case, you're taking every third, so no, no, yes, no, no, yes, no, no. You would take the next person, yes. So in this case, you're taking every third member of the population. You take every fifth member, every 30th member. It doesn't matter. So if you structure it like this, every member has an equal chance of being selected when you vary the value of k. Another method is stratified sampling. So you take the population, you divide them up into at least two groups. It doesn't have to be exactly two. Men and women, or smokers and non-smokers, or freshmen, sophomore, juniors and seniors, undergraduates versus grad students versus PhD students. Somehow partition the population into individual groups and then sample each individual group. Another method is called cluster sampling. Basically, you take the entire population. So this would be maybe a state that's broken up into individual, like 32 individual counties, and so you pull entire groups in a random way. This could be done in combination with systematic sampling. So you could, let's say this is the state. It's broken up into counties. You could take every 7th county. So like you would take number 7, number 14, number 21, and number 28. Okay, so that would be a method in which we're combining cluster sampling with systematic sampling. Either way, whenever you take a sample from the population and you calculate a sample statistic, there's going to be some sampling error because you're not including every single member of the population. So this idea of sampling error, well, sampling error is just the difference between the sample statistic and the population parameter. The only way you could guarantee your sample gives you the exact value of the parameter is if you sample the entire population. And the whole point of this, of applying these statistics, is to not have to sample the entire population. So this brings me to the next topic, sampling distributions. So a distribution of sample statistics is basically just a list of all possible sample statistics for a given sample size. For example, let's say we have a population of students and we're pulling samples of size 50. Right, so sample size equals 50. If we resample over and over, we take the first sample, we get the first sample mean. We take the second sample, we get the second sample mean. Third sample mean, and so on. So every time we resample, we recalculate the sample statistics. It turns out that no matter how the original population is distributed, so the data here could have any type of distribution, exponential distribution, logarithmic distribution, normal distribution, uniform distribution, or no distribution at all. When you start taking samples, these sample statistics, as long as you take enough and the samples are large enough, those sample statistics will form a normally distributed set. We'll come back to that a little bit later. So to give you a finite example of what I mean, here's the population. So it's a very small example. Population has only 4 numbers. So this population has a uniform distribution, 18, 20, 22, 24. Each number has exactly a 25% chance of being selected. So here's the distribution of the entire population. We calculate the mean, 21, and we can calculate the standard deviation, 2.236. So now if we pull all possible samples from this population, and in this example, I'm going with replacement. I'll talk about why in a little while, but I'm if I select the number 18 first, I could also select the number 18 second. So that means I have 4 options for the first choice, 4 options for the second choice. 4 times 4 is 16. So there's 16 possible samples. So 18 and 18, 18 and 20, 18 and 22, so on and so on. So I could list out the 24 individual samples, and for each sample, I could calculate an x bar, or a sample mean. So I'll have x bar number 1 coming from here. So the average, the sample mean of this first sample is 18. The sample mean of this second sample is 19, and so on. The sample mean of the third one is 20. So I have 16 samples, calculate 16 sample means. So the original data had a uniform distribution, but the sample means have a uniform, or have a normal distribution. There's 1 of these, there's 2 of these, there's 3 of these, and so on. So the probability of choosing an 18 from this list was 1 out of 16. Probability of choosing a 19, well, that's 2 out of 16, and so on. The probability of choosing a 20 was 3 out of 16. Probability of choosing a 21, well, there's 4 of those. So you see this following this general normal distribution, or this general normal shape. So now, if you have the entire, for a very small example like this, for the population, we could calculate the mean and the standard deviation. And then once and if we look at the previous slide, these are all, each one of these is an x bar. So this is like x bar number 1, x bar number 2, x bar number 3, and so on until we get up to the x bar number 16. So these 16 individual sample means are given here. So these are sample statistics. So think about what we're doing. We take a population. From that population, we pull many, many samples. Each sample has a sample mean. So I've listed here the 16 individual sample means. If you take the average of this set, if you take the mean of all of the sample means, you get 21, which is exactly the value of the population mean. So that this observation is leading us to believe that maybe the mean of all of the sample means is equal to the population mean. And the standard deviation of this set is equal to 1.58. We'll talk about what this number is, this 1.58. We'll talk about what this is a little bit later. Right now the point is, I'll use green here, the mean of the population is equal to the mean of the sample means. We'll use this notation here. So mu for population mean, because we've done every possible sample statistic. We've exhausted all possible samples of size 2. So mu with a subscript x bar, this notation means the mean of all possible sample means for a given sample size. In this example, we're using a sample size of 2. So the standard error, so this guy over here, sigma sub x bar, the standard error of the means, this is going to be equal to the population standard deviation divided by the square root of the sample size. So this is called the standard error of the mean, and you would expect less variation for larger sample sizes. So as the sample size goes up, so as the denominator goes up, the value of the standard error goes down. Oops. Okay. So the larger the sample size, the smaller the variation between sample statistics and population parameters. So to sum that up, the distribution of sample means has a mean equal to the population mean. That's what this is saying. The mean of the sample means is equal to the population mean. And here, the standard deviation of the sample means is equal to the population standard deviation divided by the square root of n. So as n goes up, sigma sub x bar goes down. Larger sample size means less variation in the distribution of sample statistics, or distribution of sample means. So if we plug these into our formula for z-scores, we get z is equal to x minus the mean divided by the standard deviation. So here, our x is actually a sample statistic. So we have our sample mean minus the population mean divided by the standard error. And that becomes what we have here on the right. So we're basically plugging in this guy here and this guy down here. So now this becomes a very similar situation to what we've done previously with the probabilities relating to the normal distribution. So now, going back to this idea of unbiased and biased estimators, which we talked about briefly earlier in the course, we say a sample statistic is unbiased if it estimates the value or targets the value of the population parameter. In this case, specifically for the mean, we say the sample mean is unbiased because it targets the population mean. That's what's going on here. If you have every possible sample mean, they will average out to the exact value of the population mean. So this is why we're saying that the statistic of the mean is unbiased because the sample mean targets the population mean. The standard deviation, we'll see in a little bit, does not. All right, so just overall, we say unbiased estimators are statistics that target the parameter. Biased estimators do not. So the mean and the variance and proportion, which we'll talk about later in the course, are unbiased estimators. There is a median, the range, and most importantly, the standard deviation do not target the population parameter. They are biased estimators. So now, to get to the central limit theorem, because this is really a central and fundamental theorem in inferential statistics. So the larger the sample size, the less variation in the system, and the more closely your sample statistics will act like a normal distribution, regardless of how the original population is distributed. The central limit theorem says, for any population of data, regardless of what that data looks like, any data out there, if you resample, take a sample, find the mean, take another sample, find the mean, take a third sample, find the mean, and so on and so on and so on. All of those sample means you take will form a normal distribution, as long as your sample size is large enough. And the mean and standard deviation of that normal distribution is given below. So the mean of the distribution of sample means is equal to the population mean, and the standard deviation of those sample means is equal to population standard deviation divided by the square root of n. So in this case, the mean targets the population, the mean as a statistic targets the population mean, and the standard deviation underestimates the population standard deviation. So I was saying earlier, if the sample is large enough, normally we say if the sample is larger than 30. Sometimes we could use a smaller sample size if we have some type of symmetric distribution, but to be safe, we'll use this as a threshold. If our sample size is larger than 30, then the distribution of means will be normal with, this is our mean and standard deviation. So if our population looks like this is not a normal distribution, when you start sampling, those sample statistics will start looking like this red graph here. Will start looking like a normal distribution. All right, so now to apply the central limit theorem, so calculating probabilities using the central limit theorem is similar to calculating probabilities using the normal distribution, which we've covered already. It's actually very, very similar. So in this case, we're given the population mean. We're given the population mean, and we're given the population standard deviation. In this case, we're given the sample size of 36. And the question is, what's the probability that the sample mean is between 7.8 and 8.2? So we don't know what the original data looks like. We don't know the distribution of the original data, but the sample size is 36. So the sample size is large enough that we can apply the central limit theorem. Now, what the central limit theorem is saying is that the distribution of means will be a normal distribution with the mean equaling the population mean. So that's coming from here. And the standard deviation is equal to the population standard deviation divided by the square root of n. So in this case, sigma divided by square root of n would be 3 divided by 36. So when we're dealing with samples, we're always going to have a smaller standard deviation. So our population has a standard deviation of 3, that's for individual x values. But for samples of size 36, the standard deviation drops to 0.5. So we don't know what the original distribution looks like, but when we sample, we know the means will take on a normal distribution. So that's putting us here. When we start sampling now, our means will take on a normal distribution. And if we want the probability, so this is in the last slide, what is the probability the sample mean is, what's the probability the sample mean is between 7.8 and 8.2? This is the question we're asked. So we could convert 7.8 and 8.2 to z-scores. So what we're doing here is we're taking 7.8 and converting it to a z-score. And we're taking 8.2 and converting that, over here, converting that to a z-score. So this, remember, the formula we're using is x bar minus the mean divided by standard deviation over square root of n. So we have a z-score for the 7.8, that's here. We have a z-score for the 8.2, that's here. So we get a z-score between negative 0.4 and positive 0.4. And when we convert those to areas, we get, in the end, 0.3108. So, applying the central limit theorem, it's very, very similar to what we've done previously with the normal distribution. The only difference is here. The only difference is, let's go back a bit. The only difference is here. This is the only difference between working with an individual x value and working with a sample statistic. A different formula for calculating the z-score. Once you have the z-score, it doesn't matter where the z-score came from. Okay, so that about does it for sampling distributions and the central limit theorem. I'm going to post a couple of Excel worksheets to sort of put this into action. And between these notes, the Excel files, and please read this chapter in the textbook. That should give you a pretty thorough overview of this topic. Alrighty, thank you.